All right, so this video is going to be on like combustion. Pretty much most of the stuff you need to know. So let's just start with an example. So let's say you have, well, okay, your car has octane, which is C8H, oh, 18. That is gasoline. That is chemical formula of gasoline that you put in your car. But those numbers are too big, and I don't want to deal with them. So I'm going to do methane, which is CH4. And let's say you're reacting it with oxygen plus O2. And that'll go to, let's assume it's complete combustion. So it'll go to CO2 plus H2O. So step one is to balance it. So we have one C on the left, so we're gonna have one on the right. We have 4 H's on the left, so we're gonna have a 2 there. We have 4 O's on the right, so we're gonna have a 2 there. Cool, so now it's balanced. So, will it combust? Well, the way we figure that out is we look at this standard enthalpy of formation Wikipedia page, and we find the numbers down here. So I can't draw on here, but we're looking at the 4th column in this table, which is the enthalpy of formation. So our first one is CH4, which is methane, which is way down here. Negative 75. So 1 times negative 75 plus 2 times, all right, all dipolar molecules, I think that's the right word. So like O2, H2, N2, etc. All of those have enthalpy of formation equal to 0. So this is 0. CO2 1 times, where are you? No. There we go. Carbon dioxide, we'll go with the gas, so negative 394. Plus 2. H2O. H2O, where is water? Water is here. We'll go with a gas again, so negative 242. So if we do the math, we get negative 75 goes to, I think it's 877, negative 877. So what does this mean? So this means we start at this is a graph of energy. So we start at negative 75 and we end at negative 877. Negative 877. So we go down there. Technically, we don't go straight down there. We have to overcome this activation energy right here. So what I drew is just that, but that's not what happens. We have to overcome an activation energy. And the reason for that is, well, it's the reason why the gasoline in your car is not exploding right now. It has to be compressed and energy has to be put into it such that it gets up to this point. And then it can fall either back down to where it came from or to the products. And it'll pick the option that's lower. So in this case, the products are lower. So it'll go towards the products. So but you do have to put in energy. Some reactions, they will just go straight down, but not combustion typically. Okay. So this doesn't technically look like this. It looks like that, and then you go down. Cool, and the activation energy could be like in your car, it's like the piston pushing together, which it compresses it, which heats it up, and then the spark igniter, sparking it and putting in more energy, and then it gets it up to here, and then it could fall either way. And for your car, well, this is for rocket fuel, but for your car, it'll be the same, where the right side is a bigger negative number. So it'll be lower down and it'll want to go there. Okay. So then what do you do with this? Well, all of this energy, well, okay, so the delta energy, I don't know if it's capital or lowercase, but I'll stick with lowercase. Equals 877 minus 75, which is 802. Cool. So that's how much energy this reaction produced. Now, this energy is going to get absorbed by the products. And that will turn into the products being at a higher state. We're going to assume that turns it into heat. Basically immediately does, and then sometimes, depending on your combustion long term, it would go into pressure or something, I don't know. But okay, so you have this 802. Well, okay, what is heat? So we're going to assume heat, Q, is mCp delta T. Cool. So this 802 goes into, well, let's assume it's a sum of m times Cp. I'm going to redraw those parentheses. Times delta T. So it will be mCp of, what was the first one? CO2 plus mCp H2O times delta T. Cool. Now, for most of undergrad, you can assume that Cp is constant, but it isn't constant. It is a function of temperature, which makes things complicated. But you can see the reason why you assume it's constant is because most of your problems, it's like, oh, it went up 100 degrees. So you can assume it's basically constant. You can assume it's basically like 1 point, whatever that is. But for combustion, you typically go up like at least 1,000 degrees. Well, I guess it all depends, but you go up like a lot in temperature. So you could start like here and you'd end like maybe way over here. And that's like a big jump in temperature. I gotta stop doing the dotted lines. So you can't assume it's constant. So it's a function of temperature, which makes things not fun. I'm gonna redraw this as T initial. I'm gonna redraw this T final. So in this equation, the good news is your only unknown is T final, because you have the 802, you have the M, because you will if you're doing this problem. It would just be 1 mole of CO2 and 2 moles of H2O, because they gave these units in kilojoules per mole. And then you have 3 temperatures. You have Cp, which is a function of temperature for both of them. And then you also have just temperature as itself. And there are programs. I used ease. You can also use, well, ease is probably the best one. You can write this as Cp of CO2 pressure equals some initial pressure. If it's in like a engine, like a cylinder engine, you could assume it's a pressure right before, because the instant after it combusts, you can assume it's the same pressure as the instant right before it combusts. With a gas turbine, you just always assume it's the same pressure, but you get the point. So you can assume it's the instant. So P after equals P before. Oh. And then T equals T final. I messed this up. Okay. And same with this one, but you would just change the CO2 to H2O, because it would be a different line, basically. Because like you see, it's a function of pressures. They're different pressures, it's different lines, and it's a function of temperature. And this is, I don't know which molecule this one's for, but it's also a function of molecules. So a different molecule will have a different profile as well. So all three of these things affect it. But the only unknown is T final. And it's one equation, one unknown, but the unknown appears 3 different times. This arrow should be pointed there to that CP, but it doesn't really matter, because I'm going to erase it. I'm going to erase all of it, actually. Cool. So one equation, one unknown. You can solve for temperature. It's supposed to be another parentheses there. Now, unless you're doing rocket combustion, which is what this is, like your car, it combusts. It doesn't combust just with oxygen. It combusts with nitrogen as well, because it combusts with air. Because your car just pulls in air. It doesn't separate the oxygen and nitrogen. It just puts all the air in the cylinder and the combustion happens. So what would that look like? That would look like CH4 plus O2 plus 3.76 N2 goes to CO2 plus H2O plus N2. All right, why did I do the 3.76? So if we do the ratio, so we have 1 mole of oxygen, 3.76 moles of N2. It's 1 over 1 plus 3.76. That equals about 0.21, which equals 21%. And in air, 21% by mole of air is oxygen. So that's the math for that. So if we balance this, it'll look very similar. So we're going to have 1 there, we're going to have 2 there, which means we're going to have 2 there, which means we're going to have 2 times 3.76 over here, right there, as that coefficient. Okay, so if we do the enthalpies of formation, we're going to have 1 times negative 75, we're going to have 0, we're going to have 0, I'll just write them out actually. 2 times 0 plus 3.76 times 0 goes to CO2, I think that was negative 393 times 1 394. That's fine. I'm not going to change it. Plus 2 times negative 242 plus, what would it be? Should be plus 2 times 3.76 times 0. 0 because it's 0 on this side and 0 on that side. Because it's a dipole, so it's got 0. And to prove it, where are you, nitrogen? Nitrogen, N2, 0. Cool. So we got this. So what are we going to end up with? Well, we're going to end up with the same stuff as before. Negative 75 goes to, what was it, negative 877? Yeah, 877. Then we're going to get 802 equals the sum of MCP of CO2 plus MCP H2O plus MCP N2 times delta T. So we have the same number on the left side as before. We have these two terms are the same as before. All we've done is added this third term. So how will this temperature, well, I'm gonna write T final minus T initial. Initial. All right, so let's assume initial temperature is the same. This is the same, that's the same. So what's gonna happen to the T final? Well, all we're doing is adding more thermal mass. So that's more stuff that it has to heat up. So logically, that should mean the temperature goes down, and that also makes sense mathematically because you add another term here. So this whole term goes up, which means this whole term has to go down. And the only way it can go down is if TF goes down. Cool, so that's why rocket engines want to remove the nitrogen, because first of all, almost 80% of the air is nitrogen, and nitrogen doesn't combust. The only thing that combusts is the oxygen. But yeah, so that's that. And that's the easy part. And it is pretty easy compared to freaking differential equations and whatever. Okay. Yeah, let's move on. So let's look at this equation. So we had CH4 plus O2 went to CO2 plus H2O. How do we know that all of it goes into CO2? Well, in the real world it doesn't, but this assumption that it does is called complete combustion. But if it's not complete combustion, which the world is never complete combustion, it will go into more things. And it'll go into more than what I'm going to write, but what I'm going to write is just a small example. So CO2, it could also be, some of it could go into CO2. CO2. Some of it could go into CO. Some of it could go into just C, so carbon, which is the black stuff that you get on your finger if you put it above a candle. Don't put your finger above a candle, but that is what will happen. So this is like real. Plus the H2O. And you can also split up the H2O as well. But I'm just going to split up the CO2. So you have some of it going into CO2, some going to CO, some going to C. And I'm going to just assume H2O doesn't split up, even though in the real world it does. So how do you balance this? Because that wasn't even the hard part over here. The hard part was finding all the entropies or enthalpies of formation and that sort of stuff. Yeah, so how do you even balance this? Well, let's try our best with what we have. So let's assume we have one CH4, and we'll assume A, B, C, D, E. This is actually how it's done. So let's balance the C's. C. So we have one C on the left, and it goes to 1B plus 1C plus 1D. So 1 equals, it's not, it goes to, equals B plus C plus D. All right, now let's measure, or now let's do H. So H would be 4 on the left, and it goes to 2E on the right, 2E. So based on this, we can just say E equals 2. All right, and then the last one is O. So we have 2A, O's on the left. On the right, we have 2B plus C. Cool. We have 3 unknowns. We solve for E, so E is not an unknown anymore. Actually, we have 4 unknowns, which kind of sucks. And only 2 equations, which really does suck. Oh, do we have another one? Here, I don't think we do. I think we might. I might be forgetting it, but that's besides the point. So another equation we can add is this equation. And this term on the left is called K equilibrium. And it relates these. So the way we write it would be K for CO2 equals, what would it be? It would be, well, okay. Let's write it out first. C plus CO2 2CO. Well, okay, let me underline these or box them first. I don't want to mix my stuff up. All right, so we had C for that term, we had D. For CO2, we had B. And for CO, we had C. So this will end up looking like C squared over D B. D times B. Cool. So this is another equation that we have. Frankly, oh yeah. All right. So here I only have 3 equations for unknowns, but you can add another one by doing this. But you'd have to add the H2 on the right side, and you could add another one by doing that, and you could add another one by doing that, and you'll eventually have the same number of equations and unknowns. Oh, what did I erase? D, B. But yeah, here I have 3 unknowns, 3 equations, or 4 unknowns, 3 equations. But yeah, like I said, you could just keep on writing more of these K's out and you'll eventually have the same number because, like for example, this one, it adds the H2, so that'll be another unknown, but this one doesn't add another unknown. So by then you could be done and you'll have the same number of equations and unknowns. But okay, so let's assume you wrote out another one, K whatever equals whatever. And you got it. So now you got your equations and unknowns. So, unfortunately, it is not that easy. In reality, K is a function of temperature, because you can see, like, for that K value, it increases as temperature increases, which sucks because it means that you have to add of T. So of T, and it would be a T final. The good news is it's the same unknown as over here. It's the same unknown. So you're still solving for that unknown. So once you have your four equations, for unknowns, you can plug them all in to this exact same equation. Except you won't know the 802 because now it's not all going into CO2 and H2O. So there's going to be a lot of freaking terms, but it's not terrible. It's going to be like, what would it be? It would be, so instead of the 802, I'm going to just call it delta H, even though that's probably not correct. It would be 1 times H, enthalpy of formation of CH4 plus A, enthalpy of formation of O2 minus B, enthalpy of formation of CO2 ... So that's going to be your H, which is the 802 number. And then you set that delta H equal to, what do you set it equal to? Set it equal to MCP plus MCP plus MCP, MCP. And this will be CO2, this will be CO, this will be C, and this will be water, so H2O. And this will all be times T final minus T initial. That should be it. That should be all the equations you need. It's a lot of equations, and you have to solve them all simultaneously, which kind of sucks, but it is possible. So kind of the way to do it is to pick a final temperature, plug them into here, and then you'll be able to solve for A, B, C, D, and E. Then you plug it into here, into your delta H equation, and then you plug that delta H into here, and you plug in the temperatures into the CP of T to find out what the CP value actually is. And then you can solve for T final. And if your T final that you solve for isn't the one that you guessed with, then you re-plug in that T final that you just calculated, and you do it over and over again. So you can literally program like a for loop or like a while loop or something and have it do it for you. But that is the math for it. That is all the math for combustion. It does kind of suck, but like concepts really aren't hard. And like concepts are really, really useful for more than combustion. So for example, there's catalysts also, which I might do a lecture on, but those are pretty neat as well. And knowing combustion frankly, just knowing whether a reaction, like which side a reaction will go to, the left side or the right side, that is the main part. If that's the only takeaway that you have, that's a good takeaway. But yeah, cool beans.